Yes, the next talk is by Rafael Nepomechie, Boundary Reflection Matrices of Perturbed Minimal Models. Please.
Okay, thank you, Vladimir, and thank you, Murray, both for the invitation. Very honored to be participating. Right, so this is joint work with Zoltan Bajnok and Paul, who's there. And this is work that recently appeared on the archive. So I had the privilege of meeting Professor Baxter on several occasions. The first was, back in 1991, when he came to this conference in Miami. And this is the group photo. So it was a mixed crowd, but you may recognize some of the people. There's Sasha Zamolodchikov, Jim McGuire, Michio Jimbo, Hank Thacker, Vladimir Koropin. But Baxter unfortunately missed the group photo. Barry can correct me, but I think he was out sightseeing with him. But we did get a photo. Yeah, he wasn't there. But we did get a photo with of Rodney with Jim McGuire. So that was good. I think everyone here will agree that Baxter's work has had and will surely continue to have a profound influence on every aspect of quantum integrability. And today's talk is no exception, as it is partly based on this famous ABF paper. So now the guiding example for this work is the two-dimensional Ising model. So as you all know, classical model of spins plus or minus one at each side of a rectangular lattice with this nearest neighbor interaction. So at that critical temperature, it's described by a conformal field theory with C equals a half. Below the critical temperature, there are two degenerate equilibrium states, O plus or O minus. And these are minima of the Landau-Ginzburg effective potential. And as Chico mentioned earlier, this model is equivalent to a one-dimensional quantum spin chain. So in the limit that the temperature goes to zero, and so lambda goes to infinity, then this term dominates. And you see that there's indeed two degenerate ground states, all up or all down. And then the excitations consist of kinks, whose mass can be shown to be proportional to 1 minus lambda. So at the critical temperature, lambda is 1, and the kinks become massless. And then there's an operator which creates kinks from the ground states, kink operator. So in the near the critical temperature, this model is described by a continuum quantum field theory, namely a free massive Majorana field with this Lagrangian density, and whose mass is proportional to the difference from the critical temperature. And this can be regarded as a bulk perturbation of the conformal field theory with dimension half-half. And the spectrum of the theory is just fermions with mass m, energy E, momentum P, and theta here is the rapidity of the particles. And the fields can be decomposed in terms of creation and annihilation operators, which can, and we can regard this kink operator, as a kink operator that interpolates between the two ground states. These operators anti-commute, and we can regard that as a statement about bulk scattering, namely that the S matrix is -1, which is that of a free fermion. And it corresponds to this picture here of two kinks. Now, now we want to consider the situation when we're on the half line, so from minus infinity to 0, with some boundary magnetic field H at the boundary x equals 0. So this was studied by Goshal and Zamolodchikov, and they proposed this as the action for that theory. So a magnetic field appears here. So A is a boundary degree of freedom, lives only at x equals 0. The dot denotes time derivative. And this is a boundary perturbation, turns out at dimension 1/2. And Goshal-Zamolodchikov argued that this is an integrable perturbation. And as the bulk mass goes to 0, we can identify two boundary conditions. One, when the magnetic field is 0, this is a case of free boundary conditions, where the states plus and minus are still degenerate. And as h tends to infinity, we get the fixed boundary condition, plus. Then we, still following Goshal-Zamolodchikov, they studied what happens when one of these kinks scatters from the boundary. So the rapidity changes from theta to minus theta. And so we have this so-called boundary reflection matrix. And they computed it exactly, and this is what they got, where C is related to the mass and the magnetic field in this way. You notice that reflection matrix has a pole at theta is equal to IC, which is physical in this domain. And then it corresponds to a boundary bound state, that is that the kink gets stuck to the boundary. And we can check that indeed when C is pi over 2, which here means that the magnetic field is 0, that these two energies are the same. So indeed, this is a case of free boundary conditions. The two vacua plus and minus are degenerate. So this was all old work. And now what we'd like to do is we'd like to generalize this beautiful story. So we want to go from the critical Ising model to unitary minimal models. So the central charge now is given by this. So the Ising case corresponds to the m equals 3. And then we'll swap the bulk perturbation to phi 1, 3. So the dimensions are given here. And then we'll swap this boundary perturbation by the phi 1, 3 boundary perturbation, which has this dimension. And this bulk and boundary perturbation were argued to be integrable, again by Goshal and Zamolodchikov. And the question we'd like to address are, what are the boundary reflection matrices? The case m equals 4 was already worked out a long time ago, but the cases 5 and higher were still outstanding. And also, we'd like to account for the non-invertible symmetry in this setup, which has been recently explored by these authors here. So the outline for the remaining of the talk is as follows. First, a brief review of the bulk scattering theory, and then mostly review of conformal boundary conditions and something we introduced, so-called boundary subsets. Then a brief review of the boundary scattering theory, and finally the main results of the construction of these boundary reflection matrices, and finally a brief discussion. Okay, so let's go with the bulk scattering theory. So the action is that of the minimal model perturbed by phi 1, 3, which was argued to be integrable, again by Sasha. So this model has m-1 degenerate vacua. And the spectrum consists of kinks, again with mass m, energy E, momentum P, that interpolate between neighboring ground states. So here A and B are between 1 and m minus 1. These are referred to as heights, and they must differ by 1. And they can be pictured in this way. So rapidity theta interpolating between these two vectors, A and A, or plus minus 1. So if we have the scattering of a pair of kinks, then this defines the S matrix. And it's known to be given by this formula here, where S bar is the so-called reduced S matrix. And these are the weights of the critical ABF model. The bracket here is this notation. And then U is a scalar factor given explicitly here. And there's no bound states in the bulk. So this S matrix satisfies this crossing relation. So this is a funny factor which was emphasized in this recent work. There were also discussion about this way back. Also, it satisfies unitarity. So here G is the adjacency matrix for AM minus 1. And of course, the Yang-Baxter equation pictured here. Okay, so now let's turn to the conformal boundary conditions and boundary subsets. Now, a conformal field theory can have various boundary conditions that are conformally invariant. For example, a free massless boson on the half line. So here's the Lagrangian density. So this theory, of course, has C equals 1, conformal field theory. So one boundary condition is to set the field at the boundary to be some value, phi naught. This is a Dirichlet boundary condition. Or the x derivative at the boundary to be 0. This is the Neumann boundary condition. And these are examples of conformal boundary conditions. Now, in the case of the minimal models, Cardy identified a set of conformal boundary conditions corresponding to the primary fields designated as phi RS. And here R and S should lie in this range. And by the cat stable symmetry, this is also equal to R prime S prime given here. And we're going to designate these conformal boundary conditions simply like this, R comma S. So just as an example, going back to the Ising case where we discussed this action and these boundary conditions. So in terms of Cardy's designation, this here with zero magnetic field corresponds to the free boundary conditions F, and H goes to infinity where the we'll fix to plus. Cardy denoted it as the plus. And in terms of the conformal boundary condition R comma S, this guy corresponds to 1 comma 2, and this one corresponds to 1 comma 1. Now there's a very useful graphical representation of the conformal boundary conditions for minimal models. So we draw a lattice with m nodes, and we label them 1 to m. So the edges between the nodes then will be labeled 1 to m minus 1. So the idea is to represent the conformal boundary condition Rs, if R is less than S, by the subgraph of connected nodes from S minus R to S plus R. So for example, going back to Ising, where m is 3, and for the boundary condition 1, 2, then S minus R is 1 and S plus R is 3. So it's the whole lattice, 1, 2, 3. And there's a similar prescription in the case of R bigger than or equal to S. It's the subgraph of nodes from R minus S plus 1 up to S plus R. Now, the reason I'm mentioning this is that for a given conformal boundary condition, only a subset of the heights, which are denoted by U or S, are allowed on the boundary. This turns out to be a very important concept. And we call these boundary subsets. And these uniquely characterize the conformal boundary condition. And it turns out that they're given simply by the edges of the RS subgraph. So going back to the Ising example, m equals 3, we said that for the boundary condition 1, 2, this was the subgraph. So the edges are simply 1 and 2. So in other words, the boundary subset for the 1, 2 boundary condition is 1 and 2. All right. So going back to Ising again for the one last time. So the heights usually denoted 1 plus and minus will denote them here 1 and 2. So let's make a table. So for the conformal boundary condition 1, 1, we said this is Carty's designation. So the boundary subset turns out to be 1, so plus. And for the 1, 3 boundary condition, the minus boundary subset is 2, so again, minus. And in the 1, 2 boundary condition, that's what we called free. So here, as we just said, the boundary subset is 1, 2, so both plus and minus. So it's quite natural, this boundary subset. Okay, so now turning to the boundary scattering theory. So this is the action. So this is now the action for the minimal conformal field theory with the RS conformal boundary condition. We perturb 513 in the bulk and 513 in the boundary. Again, this was argued to be integrable. So again, Ghoshal and Zamolodchikov introduced the notion of a boundary operator, B sub A. So A is the height at the boundary. Now what we can say more is that this A must be in the boundary subset for RS. Multi-kink states look like this, where the kink closest to the boundary must have the same height as the boundary. And in particular, if you have a kink reflecting from the boundary, then we have this picture, and then here we have this boundary reflection matrix. And this is the thing we want to determine. Now, it'll depend, of course, on the rapidity of the kink, and also on some parameter we'll call C, again, as in Ising, which is related in some way to the lambda and H in the action, but this is something we don't know. We'll assume as in Ising that H equals 0 corresponds to C equals pi over 2. So for sure, these amplitudes must vanish unless both B and C are in the boundary subset. Again, we want to determine these matrices, and we'll do it using bootstrap. So they should satisfy boundary crossing relation. Again, this is a funny factor, which was noted by these authors very recently. Also, it should satisfy boundary unitarity and boundary Yang-Baxter. So again, so the order of the scattering, if you have two kinks, the order from which they scatter from the boundary doesn't matter. And similarly, as in the case of Ising, we can have a kink stick to the boundary, forming a boundary bound state. So formally, we can have the boundary operator for the excited boundary related to the boundary operator at the ground state related here with a kink, and then some bulk, bound particle boundary coupling. And this boundary bound state should correspond to a pole of this reflection amplitude. And very importantly, it should satisfy these amplitudes should satisfy the boundary bound state bootstrap, which means that if you have now two kinks, one of them that sticks to the boundary and one that doesn't, the order shouldn't matter. So it can stick first and then the other one can reflect, or one reflects and then one sticks. So written out explicitly, it looks like this. Okay, so now we come to the main result, which is the construction of the boundary reflection matrices. So as I said, our objective is to determine these boundary reflection matrices for all conformal boundary conditions, RS. And what we'll see is that certain, which we'll call elementary solutions of the boundary and Baxter equation, are already known. They were worked out by Paul and Berend long ago. But these solutions do not obey this boundary bound state bootstrap that I just showed. And so the strategy will be to construct paired solutions that obey the bootstrap by forming direct sums of certain pairs of these elementary solutions. So that's the idea. Let me show you how that works. So again, the elementary solutions are solutions of the boundary Yang-Baxter equation. We'll call them reduced because they satisfy this boundary Yang-Baxter with the reduced bulk S matrix, thing I called S bar. So here they are for the boundary condition PQ. So these factors F are fused adjacency matrices. They can be either 0 or 1. It looks rather complicated. You don't have to look too carefully. The point I want to make is that they're explicitly known for all boundary conditions PQ and for all values of the heights. Now, let's define elementary boundary subsets denoted by V, PQ. Again, the subsets from 1 to n minus 1, such that an element of V, A lies in V if and only if this this F, this fused adjacency matrix is not 0, that is, it's 1. So the point is that these elementary solutions that I just showed you on the previous slide are 0 unless both heights B and C are element of this subset V. This is a little similar to what we said earlier about the the boundary subsets U, such that the reflection matrix will be 0 unless the boundary heights B and C are both in the U boundary subset. And a key fact is that this U boundary subset is the disjoint union of two of these elementary boundary subsets. This one here and this one here. Okay. So now if we take this elementary solution B bar and we dress it with some scalar factor in this way, we'll get this B without the bar. And one can show that this guy satisfies the boundary Yang-Baxter equation with a complete bulk S matrix, S, that is including the scalar factor. And it also satisfies crossing and unitarity if we suitably adjust this scalar factor, VPQ. I won't write it here. It's rather complicated. You can find it in the paper. but it does not obey the bootstrap equation. It obeys this equation. And if you'll notice, here we have PQ, and here we have something else, m minus p minus 1, n minus q. So it it mixes two different b's. Okay, so these b's cannot be the answer. So our claim is that the answer, the reflection matrix for the boundary condition Rs, is given by the direct sum of two of these b's. The b with for this boundary condition and the b for this boundary condition. In other words, this boundary reflection matrix will be equal to the first guy if b and c are in this elementary subset, or they'll be equal to this guy if the b and c are in this elementary subset. And this is well defined because, as you recall a few slides ago, that the boundary subset URS is given by the disjoint union of these two elementary subsets. So these are the, so now under bootstrap, these go into each other, but in other words, this one mixes, only stays with itself. So now all the constraints are satisfied. And therefore, this should be the right answer, and this is our main result. Okay, so then let me just conclude with a brief discussion. So if you take the general formulas that we found, and we specialize to the case m equals 3, they reduce to the ones found by Goshal and Samologikov. And if you reduce to m equals 4, they agree with those found by Chim and Miwa and Weston. But then there's still many open problems. So one is our boundary reflection matrices are in terms of parameter C, and we'd like to know the relation of this parameter to the parameters in the action, which is for the 513 bulk and boundary perturbations. So this still to be determined. Also, there's other conformal boundary conditions, namely superpositions of Cardy conformal boundary conditions. And it might be interesting to work out what are the reflection matrices for those. Also, we expect that there should be some kind of boundary quantum group symmetry for these boundary reflection matrices, just as there is a bulk quantum group symmetry for the bulk scattering matrices. And also, just like the bulk scattering matrices can be obtained by reduction from the Sine-Gordon bulk S matrix, one might wonder whether these boundary reflection matrices that we found can be obtained in some way by reducing from the boundary Sine-Gordon reflection matrix. And there's, well, many other questions, but I think I'll stop here. So thank you.
Thank you. Do you have time for a quick question? No questions?
I'll ask a question. So,
Yes.
Rafael, a long time ago, we saw that certain solutions of the reflection equations corresponded to, say, the special phase transition or the ordinary transition, surface transition. So I wonder if that's the case here as well, if there's different.
Yeah, so so those were for lattice models, right? So here we're looking at field theory.
Yeah.
So you're asking and see, those were solutions for what was the which R matrix was that for?
So Isaac and Karpman.
Yeah, so those were like vertex type R matrices, right? So here these are like RSOS models. So it's a bit different setup. but and it's not 822, it's it's kind of AM. So different models. Yeah, maybe some kind of maybe with some kind of phase boundary correspondence, one could try to map that somehow to something like this, but yeah, I don't know.
Okay, let's think again.